Hello, and welcome one and all to our last video on concurrency control. Let me lay out the agenda for what I'm going to talk about today. We're going to talk about, as I alluded to in the last video, the kind of counterpart to the pessimistic two-phase locking, and that is a non-locking based approach, or a category of approaches known as optimistic concurrency control, or OCC. Then I will talk about another kind of concurrency control that actually encompasses more than just concurrency and interacts with a bunch of different parts of how a database system functions, and that is multi-version concurrency control, very widely used. I will also talk about isolation levels. And the fact that within a database management system, we can actually often specify kind of how much isolation we're going to require it to provide to transactions. And there's a trade-off there between concurrency and isolation. And finally, I will demonstrate some of the transaction and concurrency concepts we've been talking about in Postgres. So let's start out at our optimistic concurrency control. And the idea here is that when we're doing something like two-phase locking, and we have a bunch of locks that we're requiring, and every time, for every resource a transaction is going to read or write, it needs to acquire a lock, and all this acquiring of locks leads to significant overhead. There's just a lot of extra work the transaction has to do, asking the lock manager for locks, waiting for locks, all this sort of thing. And we want to ask, what if conflicts are rare? What if, in our particular workload, for our particular application, it's very uncommon for transactions to conflict. All the transactions are being generated for user accounts, and they're only generated by one user for one account, and so a user would have to be doing something exceptionally strange where they're logged into two different places simultaneously editing their profile or something like that in order for our transactions to conflict. And so doing all this locking, all the resources that a transaction is going to lock, no other transaction in almost every case is going to be accessing those resources at the same time. And so this overhead is completely unnecessary. And so we're going to want to optimize for the common case. We're going to want to choose a concurrency control scheme that is appropriate for a situation where conflicts is rare and that is going to avoid the overhead that locking introduces. And so that's where this category of optimistic concurrency control comes in. And one major feature of at least the optimistic concurrency control features that I'll talk about and that are in the textbook is that they're going to be timestamp based, meaning that they're going to use some aspect of the time that a transaction does things in order to ensure the serializability of the schedule. So we did that with locks and two-phase locking, and for our optimistic concurrency control, we're going to be using this timestamp-based approach. And what this means is that we're going to assign transactions unique timestamps. So we're going to say something like, we have TS of some transaction A means the timestamp of transaction A, and it's going to be some unique integer that is the timestamp for this transaction. How these timestamps are generated is implementation dependent. They could use the actual system clock, but then you have to to account for time zones, daylight savings time. You might just use a kind of logical counter. The first transaction is timestamp 1, then timestamp 2. But if it's, say, an integer, if you get to like 2 billion and some transactions, then you might have to deal with integer overflow. So in practice, there's kind of some implementation details to work out, use a hybrid of these two approaches, but we're just going to have some method of assigning transactions unique timestamps. And I'll be denoting the timestamp of a transaction with this TS notation. And how we'll use these timestamps is to say that if our timestamp for some transaction A is less than the timestamp for some other transaction B, we'll say that transaction A is older than transaction B, or conversely, transaction B is younger than transaction A, and we're going to require schedules that make it so that are equivalent to the case where a serial schedule that had transaction A execute entirely before transaction B. So in practice, they can be interleaved, but they need to be equivalent to the serial schedule where transaction A happened and then transaction B happened. And so that our schedules will kind of obey this timestamp ordering, that a transaction with an older timestamp, the outcome, the effect will be as if that transaction happened first. All right, so there's an approach to this optimistic concurrency control called timestamp ordering. And the general idea here is that on every operation, we're going to check the read or the write timestamp, the timestamp of the transaction that most recently read or wrote to some object that we're accessing, in order to check, okay, is this current access that this transaction is doing, is that valid with respect to the last read or write timestamp? So if an older transaction is writing to some piece of data that was read by a younger transaction, that's a problem because that write was not seen by the younger transaction, and thus we're not enforcing this kind of serializable property that we want. And so we'll use these checks of each data access and these timestamps to know when a transaction has encountered a conflict and needs to abort. Now, that's all I want to say about timestamp ordering because in practice it's not very commonly used. And instead, I want to focus on a similar type of optimistic concurrency control, which I'm not in charge of naming these things. The type of optimistic concurrency control that I want to focus on now is called optimistic concurrency control. So we have a specific protocol called optimistic concurrency control, which is an example of a protocol in the category of optimistic concurrency control. Look, I don't know who named these. This makes no sense, but it is the actual terminology. So what distinguishes our optimistic concurrency control protocol is that it is validation based, which means we're going to let our transactions kind of execute all the way through, and then when they are ready to commit, we will go through a validation process to make sure that there were no conflicts. And just to be clear, our optimistic concurrency control, I mentioned earlier non-locking, our transactions are not acquiring any locks. They're just going right ahead. In the timestamp ordering, they're checking these timestamps of these operation with our optimistic concurrency control, just no checking of any kind until that validation phase. So let me illustrate what I mean with an example. All right, so in this example, we have two transactions, transaction A and transaction B. And transaction A reads and writes some resource A. Transaction B reads A. And so what our optimistic concurrency control protocol will do is that each of these transactions will go through 2 or 3 phases. And these phases are named read, validate, and write. Now, the read phase is a bit of a misnomer because it can include both read and write operations. And so you might think of read more as a work phase, where it's when a transaction will do all of the reads and writes, manipulating all the data. It will validate that, and then only at the end will it actually write changes back to the database. But if it's not writing changes back to the database, what is it writing in the meantime? Well, let me show you. We're at the start of our transaction, and it reads A. And when we read something in our optimistic concurrency control, we're going to make a copy of it in a private workspace for that current transaction. So when we read A, we're going to create a transaction A workspace that gets A and 1, 2, 3. So we get the current version of that resource, which I've given the value 1, 2, 3 in the database, and bringing it into this private workspace ensures repeatable reads. One of those concurrency anomalies that we want to avoid is the unrepeatable read. Right? We read the same data multiple times without making any changes to it within that transaction, and we read different values. That's breaking isolation. That's getting information from some other transaction that changed in the meantime. So by copying it into a private workspace, we're going to have a version of it that's going to remain consistent through the entirety of the transaction. So that's reading A here. Now transaction B reads A, and so it's also going to get a workspace. A, 1, 2, 3. Transaction B workspace. And now we get to the validate of our transaction B. And now here's a crucial aspect of our optimistic concurrency control. We assign our timestamp at the validation phase. So a transaction that has not reached its validation phase does not yet have a timestamp, and its timestamp is viewed as effectively infinity. So once we get to our validate, we're going to say, all right, timestamp of transaction B gets assigned to be 1, let's say. We're just starting off at 1. So now transaction B has timestamp of 1, and at this validation phase is when we check, are there any conflicts? And so all we did was read A, nothing else was writing to it, at least at this point, so everything looks good, and we let transaction B go ahead and commit. It didn't do any write operations, so there's no changes from its private workspace that we need to propagate back to the actual database. So we're done with transaction B, we throw away its workspace. Now we continue with transaction A. It goes ahead and writes A. Let's say it updates it to 456. It goes to validation. We assign it a timestamp at that point. Let's say we just assign it 2. And now we're saying, all right, are there any conflicts between transaction A and other currently running transactions? Well, in this picture, there are not any other active transactions at the time of validation. Transaction B is already committed and finished, so we don't have any conflicts. Transaction A is valid. At that point, changes that were made in transaction A's workspace are written back to the database. That's this write phase. And so now we would update our database, tab A, 3, 4, 5, 6. So these three phases, read or work, validate, and write, are the structure of this optimistic concurrency control protocol. And as I said, we're going to, at validation, check the validating transaction against all other currently active transactions, not those that already finished, not those that haven't started, but the other currently active ones. This is not the only way to do validation. You can also check only against previously committed transactions rather than those that are currently running. And one simplifying assumption that I'll make for the purposes of this lecture is that only one transaction can be validating at a time. In actual systems, they will find kind of clever and careful ways to allow parallelization in the validate phase, but that is something that can be a bit complicated. All right, so how do we actually decide if a transaction is valid? It was pretty easy here, but there are more complicated cases, and let's go through them. Okay, let's talk validation criteria. So let's say we're validating some transaction Ti, and we want to check against some other transaction or set of transactions, Tj, that are active when we go to validate Ti. So the different criteria that we might have to say a transaction is valid is, number one, Ti does everything before Tj. The transactions are just actually serial in our schedule. We see Ti does its read, validate, write, then Tj does its read, validate, write, and we're good. There's not going to be any conflicts when the transactions are just actually serial in our schedule. So a more interesting case is where our second case is when Ti completes before Tj gets to its write phase, and it's the case that Ti did not write to anything that Tj read. And I've written that out here as the set of writes, the write set of Ti, intersection, the set of reads from Tj, is the empty set. So there's no overlap between what Ti wrote to and what Tj read from. Now remember that we're going to be validating against all other currently active transactions that will themselves not have been validated yet. So they're all going to have timestamps greater than Ti, so other kind of younger transactions. And we want to make sure that nothing that the transaction we're validating, Ti has written to its private workspace, is something that would affect, that would be read by, or has already, in fact, has already been read by the other active transactions. So then they will not have seen the update made by Ti, and their effects will not be as if we had this serial Ti and then Tj. And so let's look at this example over here, that we have our Ta, it reads A, we get its private workspace with A, 1, 2, 3, and then it writes A, updates it to 4, 5, 6, then transaction B reads A, it's 1, 2, 3, and then we go to validate our transaction A. So at this time, we give it a timestamp. We'll say it's timestamp 1, and we're going to check against all other Tj that have greater timestamps. Transaction B hasn't validated yet, has a timestamp of infinity, and so it's one of the ones we need to check against. And so we're going to say, all right, did Ti do everything before Tj? No. We have transaction B has already entered its read phase, so they do overlap. So how about this second criteria? Ti is going to complete before Tj gets to its write. That we know. We're going to get to our kind of write and commit once we go from this validate, and TV has not reached its write phase. But if we look at the set of writes that Ti has done, it has written to A. And if we look at the set of reads that TB has done, that also includes A. So there is overlap, and so TA is not a valid transaction under this optimistic concurrency control, and we would need to abort because we don't have any way of knowing at this point that this is because our transaction B has read a stale value. It has read a version of A that would not exist if TB were actually executing after TA. And so this is how our optimistic concurrency control is enforcing the serializability of our schedules. All right, so this is kind of our overview of our optimistic concurrency control, and it's going to allow our transactions to proceed without acquiring locks, to proceed with less overhead, and because we're assuming that conflicts are rare, when we get to this validation, we check against other currently running transactions, and we're thinking, well, most of the time we won't have to abort, and life will be good. So there are some potential drawbacks to this optimistic concurrency control. And so one of these is that we've introduced a different kind of overhead. Right? We're always copying the data that we read into a private workspace in order to ensure repeatable reads, and that could be expensive. We now have, instead of acquiring locks, we have some overhead from copying. We also have some points in this protocol that are potential bottlenecks. So, as I said, we were assuming that only one transaction was validating at a time, but even if we allow that to happen in parallel, it's still possible that synchronizing, the synchronization we'd have to do in that case would still create a bottleneck at the validate or write step, and also potentially we could have a bottleneck when allocating timestamps because we need timestamps to be global across all our transactions. They have to be unique, they need to be monotonically increasing, and so our timestamp allocation could become a potential bottleneck where a bunch of transactions are waiting for their timestamp because they can only, that has to be synchronized. It's also the case that our aborts could be more expensive than in two-phase locking because it's not until we get all the way through our transaction that we go to validate and then potentially abort. And so if we do end up aborting, we're often going to be throwing away more work than in our pessimistic concurrency control, where if we hit an abort, it was somewhere in the middle of the transaction and less work is potentially lost. And so this is where we're going to move on from our optimistic concurrency control to our multiversion concurrency control, because this is a really elegant and widely used technique for kind of addressing this same issue that we were addressing with copying, having transactions copy everything into their private workspace, and then in fact, if our database does multi-version concurrency control, then perhaps that copying is not as necessary. We don't need to do as much of it. And so in practice, these two are combined in many systems, or our multi-version concurrency control is combined with the two-phase locking. And I'll talk more about that as we get into our MVCC. So let me clear off the board here and we'll get into it. Okay, so here's the key idea behind our multi-version concurrency control, which is that we're going to have multiple physical copies of single logical objects. So there might be a tuple or a page or a table that we have. There's the single logical object within the database, but we'll maintain multiple physical copies. And by maintaining these multiple physical copies, this will mean that we no longer have to worry about our read-write conflicts, because if there are multiple versions, then an update can introduce a new version, while reads could potentially read older versions, and thus be kind of consistent with some serial schedule. And so the big win here is that our readers reading some object won't block writers, and similarly, writers won't block readers. Now, this doesn't. Now, we've prevented interference from readers with writers and writers with readers, but we still need concurrency control for write-write conflicts. So if we have two transactions that are concurrently updating the same object, we're still going to need some concurrency control in order to resolve those write-write conflicts. But before I get any deeper into this, I want to illustrate what I mean with an example. Okay, here's the situation. We have transaction A, read and read A, transaction B, writes A, and we have our database with some objects that I've called A0, the version 0 of our resource A, value 1, 2, 3, and for each object in our database, we're going to keep track of a begin timestamp and an end timestamp. So these two things here, they are these timestamps, and so our current version of A valid from timestamp 0 through infinity. And when we begin a transaction, we're going to assign them there's not a validation phase necessarily, and not at all in this example. So when a transaction begins, that is when we will assign it a timestamp. And so when we begin A, we say, all right, timestamp of transaction A is 1. We read A, and so it goes to the database and says, all right, I have a timestamp 1. What version of A is valid for timestamp 1? Well, there's only one version of A. It's valid from 0 to infinity. So we go ahead and read our value 1, 2, 3. Now, our transaction B begins. It gets a timestamp of 2, and it will write A. And so it is going to write a new version of A. I'll call it A1. And it says the value is 4, 5, 6. And now it updates and this transaction that's writing A is timestamped 2. And so this has a valid from timestamp 2. But any transaction that has an older timestamp will not get to see this version, because it's only valid starting at timestamp 2. At the same time, this also needs to adjust the end timestamp of the previous version. So our A0 is now going to end at timestamp 2, and then from 2 onwards, we're using our version A1. And so then when our transaction A reads A again here, goes to the database, and again is looking for the version of A that is valid for its timestamp of 1. And so again, it will read the old version of A. So this read got A0, this write produced A1, and then this again read our A0. And so our multi-version concurrency control here provided the isolation to these 2 transactions by maintaining these multiple copies of our object A. All right, so let's do a slightly more complicated example where what we're going to do is have our transaction A read and write A, and then our transaction B is going to read and write A, and then our transaction A will read A again. All right, and we're going to start just with A0, like we did in the previous example. And so what will happen now, we're going to begin our transaction A, timestamp of 1. We read and write A, and all right, we are going in a new version, A1. It's 456. And it begins at 1 because that's the timestamp of transaction A that just did this write. And so we'll set the end of our first version to 1 there. And so then when transaction 2 reads A, it is going to read the A1 or A0. It's actually a bit ambiguous. Because if we just look at, well, which of these 2 is transaction B's timestamp valid for, we say, well, that's A1. It has timestamp 2, and 2 is between 1 and infinity. But if we think about our isolation property, the acid properties that we want to provide, it shouldn't be the case that transaction B can read uncommitted data from transaction A. Transaction A has written this update, but it hasn't committed yet. And so which of these 2 the transaction A will read, or which of these 2 transaction B will read at this point? Actually depends on what isolation level our database is providing. And so we're going to jump down and talk about isolation levels here, and then we'll get back to more details about multi-version concurrency control. So database systems want to provide kind of flexibility and performance for different kinds of environments, different kinds of needs that users might have. And so up till now, we've been focusing on, let's make everything completely serializable. Let's ensure to the fullest extent the ACID properties of our transactions. And let's make sure that there are no concurrency anomalies of any kind. No dirty reads, no unrepeatable reads. And so we might want to, in some cases, relax these requirements in order to get more concurrency. Then we say it's actually all right if we have unrepeatable reads, and because that's all right, is if we can get the database system to relax its constraints, we can get more concurrency and thus better performance. And so database systems will provide different isolation levels that you can set a transaction to, which will determine things like which of these two will our transaction be read. So what are these isolation levels? The strongest is serializable, and so serializable is our full-on ACID properties. It's going to say, all right, obtain locks on everything immediately. Use our rigorous two-phase locking, so don't release any locks until commit. And then we're also going to lock indexes or tables in order to prevent something called a phantom read. So imagine a scenario where we want to select max of some value from a table. And then in the meantime, so we select max and we say, oh, the max is 34. And then some other transaction inserts 72 into our table. And then we again ask, all right, what is the maximum value? And now we get something different. We get 72. And so this idea of the phantom read is we have some query that goes over a range of tuples, and in between two queries that in theory go over the same range, they actually go over different ranges. That in between these two, there's been an insert and it has changed this result. So our serializable isolation level says, all right, we're going to lock tables and indexes in order to prevent this phantom read. That when we're doing this, we're not going to allow these inserts to happen. So that's our serializable level. Our slightly less strong is the repeatable reads isolation levels, which is everything that serializable does except this locking indexes and tables. So repeatable reads does allow phantom reads. Next, after that, we have our read committed. So this allows phantom reads, and in particular, it's going to additionally release our shared locks immediately which is going to allow unrepeatable reads. So our read committed, as the name suggests, is going to allow our transactions to read data from other transactions that committed in the middle of the current transaction. So this is not providing our capital I isolation from ACID, but by releasing these shared locks immediately, we're going to get more concurrency. And so if it's not going to cause us problems to have these unrepeatable reads to read data that got committed in the meantime, then this might be appropriate and could result in better performance. And finally, at the bottom we have read uncommitted, where we're just going to not acquire shared locks at all. And so we're going to read any writes that happen, committed or not. Any writes that happen during a transaction, we can read them. And so kind of this would allow, of these four, we kind of get more concurrence as we go down, but also more concurrency anomalies become possible. And so it just depends on the specific application whether that trade-off is worth it. This is all to say that in this example of multi-version concurrency control, whether this reads the initial version or the kind of uncommitted information from our transaction A depends on if we're on these first three levels, then we would need to read the original. If we're on this read uncommitted, then we could read A1. If TA committed between when TB started and when it read A, then read committed would allow us to read the update from A. And as I'll show in the demo, we can actually tell a database system for a particular transaction which one of these we want it to do. Not all database systems follow these isolation levels exactly as they are defined in the SQL standard. For example, in Postgres, read uncommitted is not a thing. If you tell it to do read uncommitted, it will actually do read committed. Similarly, there are things that serializable does that repeatable reads does not in Postgres, but because of how Postgres implements repeatable reads, phantom reads don't actually happen under that isolation level. All right, so that's our detour on isolation levels. More when we get to the demo, but for now, let's go back to our multi-version concurrency control and continue with our example here. So in this case, we don't read A1 because it's not committed yet, and so we'll read A0, and then when we write, what will have to happen is we won't be able to write A until our transaction A has committed. This would be enforced with a lock of some kind. If this were to stall, if we were doing this under optimistic concurrency control, then we would write A, and then when we got to the validation phase, we would detect that something had gone wrong. This read, however, this will read A1 because transaction A can see the updates that it itself has made to a particular object. And finally, when we actually allow this write to happen, we would get another version of A789, and we'd set it, and we'd update the timestamps as well. And so this is would be the final state of our database. We'd have 3 versions of A with the timestamps set appropriately based on the transactions that modified them. All right, so I hope that gives you a sense of what this multi-version concurrency control is about. We have these multiple physical copies of this same logical object A. And this is, as I've said, an extremely widely used technique and is part of basically every modern modern database system. And something that's interesting about our multi-version concurrency control is that there are many different design decisions that go into it. So let me clear this off a bit and go through what those are. So as I've already alluded to and mentioned, the first of our design decisions would be a concurrency control protocol that our multi-version has allowed kind of writes and reads not to interfere with each other by maintaining these separate versions, but having simultaneous writes, we still need some way of deciding which write actually happens first or which transaction gets aborted, and that's where the concurrency control protocols that we've previously talked about, two-phase locking or optimistic concurrency control from today, or timestamp ordering, any of those we might use in a system that implements our multi-version concurrency control. Another design decision is version storage. How are we actually maintaining the information about these multiple physical versions, and kind of how do we find which one a transaction should use? I kind of drew a table that had multiple of these in it. Let's actually talk about different particular ways we could implement this, this version storage. So first, we might have an append-only storage. And this is one where we have all the different versions, sort of like I drew on the board previously, all the different versions of an object mixed together in the same table. So it would be as if we had something like we have our A0, and its value is $111, and then we're also going to maintain a pointer along with each version that's going to tell us the next version, and we'll basically have a linked list of the different versions of a particular object. So A0 is 111, A1 is 222, and A0 has a pointer to find A1. And so to look up a particular version, you'd start at the head of the list, and then you'd traverse down it until you found the appropriate one. I'm omitting here the kind of begin and end timestamps that I drew earlier, but those would be included as well. And we might have some other piece of data B1, $10. It's the only version currently, so it would have null for the pointer. Notice that we don't have a B0, and this is something this is a design decision further down this list, but we're going to need some way to get rid of old versions that we don't need anymore. So in this example, we had a B0, but we've cleared it out. And so then let's say we go to update A. We have another update to A. So we don't overwrite the current version. We add another physical copy. So we have some A2, 333, and then we would update the pointer for A2 to lead us to A3. And I have this kind of chain of three versions of A. And so this is append only because we just have it all together, and whenever we get a new version, we just put it into some free space in that table. So here I've ordered this version chain from oldest to newest, right? We start with A0 and we follow the pointers down to the newest. And our version chain can be old to new. It can also be new to old. So we could have the start of our linked list be the most recent version, and then we go back to find the older versions. So when we have old to new, we have to traverse our version chain, our linked list, in order to find the version we're looking for. If we have new to old, then new transactions will be able to just take the thing at the head of the list. They won't need to traverse through it to find what they're looking for. But one important thing is that if we have indexes in this picture, they're going to be referring to the most recent version of a particular object. And so depending on whether we're doing old to new or new to old, we're going to need to be kind of updating our one important thing about this picture is that our indexes are going to refer to the head of these chains. And so this also means that if we were doing old to new, the index will always just be pointing to the oldest one, and when we add new ones, we don't have to change that. But if we have new to old, and then anytime we put a new one at the head of our chain, we have to update the index pointer as well. So they're basically trade-offs between these two orderings that might depend on how often your transactions in practice need to refer to old versions. All right, so that's append-only storage. We have another possibility, and that's time travel storage. And so this is perhaps not as exciting as it sounds. We don't hop into a time machine and perhaps a hot tub of some kind. What instead means that we're going to keep the most recent data in the main table. That our main table, we have our most recent version, say A2, 333, and B1 with 10. And then we'd have a separate time travel table that would let us look into the past, and that's where we would have the old versions. So this time travel table is where we have a 1, a 0, and a 1 with their 111 and 222. And it's our main table would have a pointer to the time travel table that had the old entries for our for that object. And then let's say we update A2 to A3. We would replace, we would first, the first thing to do would be to take the entry in the main table and put it in our time travel table, which, by the way, would still have the pointers from that we saw with the append-only storage. So we copy A2 over to here, update these pointers, and then we would update the main table to have this new version A3 with maybe $444. And so this way we have the old versions kind of in a separate separate table. So again, depending on the workload, how often we're needing to do lookups of old versions, kind of our main table is going to be smaller, so kind of more memory efficient for our buffer pool. We won't be kind of bringing in a bunch of old tuples as part of the main table or old objects of whatever kind. But if we are doing a lot of lookups into this time travel, that may be made slower. So kind of one variation on our time travel storage is what is called delta storage. And all this means is that instead of the full object in each of these cases, each of these old tuples, we're still going to maintain a separate table for information about old versions. Although it's not really a table, it's more a kind of storage, because what we're storing in this are not the actual objects, but rather the delta, the difference between that object and the newer version. So in this picture, what we store is that, all right, the value should be $111. For this one, the value should be $222. For this one, the value $333. And so if these objects had kind of a bunch of other information that was part of them that was not changing with each of these, that it was only this like one value attribute that was changing each time, under our append only and time travel storage, our additional physical copies were a full copy of the object. So that is potentially wasting a lot of space copying parts of the data that aren't changing. If we're, say, only updating a single attribute. With this delta storage, we're just storing the information we would need to reconstruct the old version by applying that delta, by applying that difference to the current version. And so this can be a lot more space efficient than these other two possibilities. All right, so these are our set of design decisions around version storage. Delta storage seems like a clear winner. Postgres and does append only. I would say append only and delta storage are a lot more common than kind of the time travel storage. That if you're storing things in a separate place, then the delta storage seems like a pretty clear win. All right, so let's move on to our next design decision. All right, next up is garbage collection. How are we going to identify and throw away these old versions when we don't need them anymore? The goal of this multi-version concurrency control is not to maintain copies of every state every tuple has ever been in through the database. That is not what we're trying to accomplish. Rather, we're trying to keep around just those old versions that we need to provide isolation between transactions. So our garbage collection kind of has again different approaches that we might take. So approach number one would be tuple level garbage collection. So this is, we want to find versions to discard by examining the tuples directly. And there are sort of two within this tuple level, there are kind of two approaches that we might take. So one we would call background vacuuming. And so what this would look like is, let's say that we have some tuples. We have A version 100, B version 100, and B version 101. And we have a begin and an end for these. Let's say A and B100 begin at 1 and at 9, and our B101 begins at 10 and ends at 20. And we have a couple of transactions currently running on our system. We have transaction 1, which has a timestamp of 12, and I have some other transaction that has a timestamp of 25. And so this background vacuuming says we have background threads, which means we have threads sitting around that are being occasionally run in the background that are not part of a specific transaction. They're not executing operators, anything else. They're just, we're keeping it around to occasionally have them run something in the background. And they're periodically just going to scan through data and check for garbage, check for old versions of the data that we aren't going to need anymore. And so they would say, check this example table that I have up here, and say, does any of it need to be vacuumed up? So they would go through and say, all right, A100, our transactions running on the system are 12 and 25. So the minimum transaction timestamp is 12, and so it cannot access any data that ends before 12. So we're looking here, and right, well, this is begin 1, end at 9. We don't actually need this. We can throw that away. Same with B100. It's 1 to 9. We don't need that either. It's garbage. B101 from 10 to 20. That our current transactions could conceivably access. And so this is just a periodic background practice, process that will go through and clean up the data like this. So the alternative is something called cooperative cleaning. And this says this cooperative cleaning says our worker threads. This means threads that are part of some transaction. They're part of some operator that's in the query. So when we have threads doing other work, so in our background it was threads that were specifically for this cleaning process, for this cooperative cleaning, threads that are doing other work, when they are when they are traversing the version chain, going through following the pointers through different versions, at that time they will check, do we need to reclaim, can we throw away this particular version? And so this is only going to work with this old to new ordering of our version chain, because they're going to need to be traversing the old versions in order to check them. If we start with the newest, they're going to stop once they get to the version they need and not check the older ones. So to give a visual example, we have our version chain of A0, A1, A2, A3, and our thread T1, let's say that it wants to retrieve A, which it does by going to some index, and then this index, remember, refers to the head of our chain. And so our transaction is that, all right, I want to get the thing that's at A, it uses this index, we go to our chain. And so now we start traversing down the chain of our different versions. And again, checking the same thing. All right, is this version so old that no current transaction could access it, and we can throw it away? And we say, all right, yes, A is too old, go to A1. Okay, A1 is also too old, we don't need that. A2, that's the one that we want. And so at this point, we reclaim the space from A0 and A1, and then we need to update the index to refer to the new head of our version chain. And so this cooperative cleaning is, all right, threads that are already doing work will kind of help out, will pitch in with cleaning up our old versions by when they traverse some chain of versions, throwing away those that we don't need anymore. All right, so these are the three main design decisions that I wanted to talk about. There's some complexities that get about how indexes fit into this whole picture that I will omit here for reasons of time. I guess the other approach to this garbage collection that I should not forget to mention is a transaction level garbage collection, and this just says that transactions are going to keep track of which older versions they use, which ones they need, and then at commit. So when a transaction then goes to commit, then the database system will check, okay, is this the last transaction? Is this the last transaction that is using this particular version? So we have these two different approaches for doing it on a kind of tuple by tuple, object by object basis, but we can also just have transactions keep track of which versions they're using. All right, so with kind of our optimistic concurrency control and our multiversion concurrency control, we've discussed through those. I talked about isolation levels. So now it's time to take a look at a demo. So let us bring up the screen. Oh my, infinity. Let's get rid of that. All right, so here we are in Postgres. And as I said, we can just start off a couple of transactions in this Postgres. And these are both going to be doing something with this tiny little demo table. Just has ID, value, two tuples, 100, 200, and 2 and 100, 1 and 100, 2 and 200. And so the first thing that I wanted to show is that if I to show the sort of to show how Postgres uses multi-version concurrency control. So if I update demo to set the value to 150 where ID equals 1. I can see that has happened in this transaction. And if I go over to this other one and select star from demo, it still sees the original version. So it's 1 and 150 over here, but 1 and 100 over here. And so this is this isolation that these multiple versions of this same tuple are providing. Similarly, I can update demo set value equal to 250, where ID equals 2. And if I select star from demo, I see that change, which of course is not reflected in the other one's version. So we have this nice isolation. But we can proceed to do something foolhardy and have our first transaction over here try and update the value of this other tuple, the one that has been updated elsewhere. So let's set value to 250, or rather to 50, where ID equals 2. And so this transaction is now waiting. Why is it waiting? Well, our other transaction modified this, and so it has acquired some sort of lock on that tuple, an exclusive lock, where now when this one tries to write to it, it needs to acquire that lock, and it's waiting. So we are not seeing evidence of an optimistic concurrency control because our transaction is blocked. It is waiting, which optimistic concurrency control avoids. But we can go one step further and try and set to 350, where ID equals 1 over here. And at this point, Postgres can detect that there was a deadlock between these two, that they were each waiting for a lock on a tuple that the other one had. Prints out a message that the process was waiting for a lock, and it was blocked by this other process. And it says it was waiting for a share lock. I think that's because it first tries to acquire a share lock, and then if that succeeds, it escalates that to an exclusive lock. But in any case, it detected the deadlock. It stopped this. It let this update go through. So I can now see that my table over here has the updates. If I try and do anything in the transaction that was stopped, really will say that the transaction is aborted, and it's just going to ignore it until the end of the transaction. So I'll go ahead and abort both of these transactions, and so we have some isolation, and we have and we saw that it can detect. There is deadlock detection, which we talked about in the last video, running in Postgres. So let's now take a look at the isolation levels that I was talking about before. And so if I begin a transaction, I can tell it to begin transaction isolation level read committed. So if you remember, we had our read uncommitted, then read committed, repeatable reads, and serializable. So repeat committed, we want to check, does that actually let us see committed information from other transactions? So let's see, over here I'm going to update demo and set the value equal to 150, where ID equals 1, and then I will have this one update demo set value equal to 250, where ID equals 2, and just make sure that it, like before, neither of them sees the update from the other. But now, if I commit one of them, we can now see that update in the active transaction. So that's what this read committed isolation levels is allowing, is that this active transaction to see updates from another transaction that committed in the middle of it. All right, the last thing, go ahead and abort and clear this out. The last thing that I wanted to show was how Postgres actually will enforce serialization. So, or rather, how the isolation level determines whether Postgres will enforce serialization. So, I'm again going to begin our both transactions in our read committed, and then here I'll be using a slightly different table. One that has two things which are class 1, 10 and 20, two things which are class 2, 100 and 200, and this is so that I can do something like I want to insert into this table the results of selecting a class of 2 and the sum of the value from demo 2 where class equals 1. So what this SQL statement is doing is it's summing up the things from the table where class is 1, so we're going to get 10 plus 20, and then inserting the tuple with a class of 2 and that sum into our table. And so now if we select, we see that has been inserted, and then in our other transaction, we insert into demo 2, and here we're going to do a class of 1 and the sum of the value where the class is 2. So now if I look at demo 2, I've inserted a tuple that is 1 and 300. So we have not seen the updates from either one, but where class is 2 would include this insert that happened in my first transaction. And so this is actually a non-serializable schedule. We have a phantom read where if I commit this first transaction and then do this insert again, I actually get 330 the second time, or I got 300 the first time. So running at this read committed isolation level has allowed this phantom read. I can commit this as well, and and under this read committed isolation level, everything can go forward just fine. And there's and Postgres doesn't do anything about it. So I'm going to restore my demo 2 table to its original glory, and now I want to do the same thing, but I'm going to tell Postgres to not allow to make sure that the only transactions that are allowed are those that are serializable, and we can see what happens. So I'm going to do the isolation level serializable instead of read committed. And I'll do the same inserts as before. We'll insert this one over here. And now if I try the same thing where I've done these two inserts and I can commit, first one commits fine, but when I go to commit the second, Postgres says, all right, you are trying to commit something which would result in effects to the data that could only come from non-serializable schedules. And so it's just not going to let me do this, and it aborts the transaction. It even tells me if you retry the transaction in isolation, then it can go through fine. So this was hopefully a somewhat interesting demo of how these concepts that we've been talking about actually play out in a real system, and give you a sense for how that is working. So from here, the next video will be on logging, and after that we'll get into crash recovery and how we actually use the disk to be able to recover the database when things go down. And then our final video will be on kind of the parts of database systems which we have not gotten to kind of give an entire lecture to as part of this course. And with that, I look forward to your questions. Wait a minute. What? Oh no. Oh, I think the void's in there. Oh, it's alive. It's sucking me in. No, I don't want to. I won't.
I'm sorry, Dave. I'm afraid I can't do that.